today we'll talk a little bit about our experience with unfitted finite element methods, trying to solve somehow large problems. So first, a little bit of motivation why we started to work on this topic. Somehow, nowadays, when we try to solve problems in our simulation pipeline, we have the main generation, which usually involves unstructured meshes when we have engineering problems with complex geometries. Then the second part is to take this polyfitted mesh and do the partition in order to take parallelism out of this. And usually this part is hard to parallelize, and graph partitioning is another one that has a very poor parallelism. So these two parts, let's say, are a real bottleneck in our simulations. Then we have to do numerical integration, let's say finite elements, integration in time. This part somehow is comparatively parallel. Here it is not much an issue. And finally, we have to solve probably nonlinear solvers. Here there are lots of weakly scalar algorithms, as the ones that we usually use, multi-level mini composition, but also very, very scalable multi-grade implementations out there. So it has been our previous work. And I would say that now we wanted to solve a little bit the bottleneck that we have in this previous part. So with regard to the linear solver in our group, what we do is to use the mini decomposition. I would say that the mini decomposition is more than a linear solver. It's a framework, like the divide and conquer framework. And it's not general purpose. It's not like a black box in which you put your matrix and you get solution. Everything is very related. The linear solver, the integration part and the linear solver part are very, very coupled. For instance, when you go to Maxwell equations, even for the solver part, you need to define, to do some integration. So everything is very coupled in our simulations. Usually we use multi-level mini decomposition methods. The idea is that we have subdomains at different levels in order to go to very large scales. And at the end of the day, what we have to do is at all levels, the idea is that we have to solve only local problems in subdomains. Okay, so this is the main decomposition in a very, very fast way. Here, for instance, these are the type of results that we get with our machinery for body-fitted meshes. This is an example for a Passion problem, which we run in the European supercomputer. And here we have 500,000 processors and almost 2 million subdomains, about 100 billion unknowns. And you see this is the computational time. So you see that even with a ridiculous problem at every one of the processors, 1,000 elements, we have this very nice weak scalability. Weak scalability means that as you put more and more processors, you do the problem larger and larger and larger. So here we are putting more processors and solving larger and larger problems, but the time remains almost constant. Okay, so this part was nice, but when we want to deal with the second part, which is to improve a little bit the mesh generation, some situations will appear. In order to eliminate, let's say, somehow the body-fitted mesh generation, we wanted to use of-tree meshes. When we have to deal with problems in which the geometry is simple, the situation is not difficult. We have interfaced our solver, our framework with pforest, which is a highly scalable of-tree-based library, which provides us mesh generation, mesh partition, with the space-filling curves, and 2-1 balance, and it's extremely scalable. You know, we can go to hundreds of thousands of processors, and you get this very, very nice scalability. So here you have a space-filling curve, which is the key. Why this is so fast when you have to balance? It is that, let's say that you put a line that crosses all the cells in your tree mesh, and then the partition is, let's say, like a 1D problem, so it's very, very efficient. But the problem is that when we want to deal complex geometries, we have to do something, which is this talk, which is the use of unfitted finite elements. This was our first motivation. The second motivation why we started to work on this was that we are in fact involved in some European projects in additive manufacturing. And in these problems, we have a geometry that's growing all the time. It's growing in time. So it's difficult to think that we're going to have a mesh that's going to be body-fitted at all time steps. That's something that's quite hard. So we wanted, for this, we were also interested in using this kind of unfitted finite element techniques. These were the two main motivations for this. Everything that I'm going to present here is implemented in FEMPAR, which is the code that we developed, which is in the Haiku Club of the most scalable scientific codes in Europe. And as I told you, the key is that we have a very advanced multi-level finite element framework in which we can use grad-conforming finite element, but also deep-conforming, Rabiat-Thomas, or Kuhl-conforming Nedek elements, edge adaptivity, etc., etc. So when we go to unfitted finite element methods, that's very simple. But the idea is that instead of using body-fitted meshes, we want to use unfitted meshes. And as you know, there are some issues that have to be treated here. The first one is how we're going to impose the period boundary conditions. I don't want to do anything new here. I'm going to use an Nietzsche type weak imposition of boundary conditions on the boundary, let's say. For this part, I don't want to do anything special. Then the other part is numerical integration on the cells that are being cut. Here, we need, let's say, a level set function. When we have a general cut and we want to insert in compute the interaction, let's say the intersection between the cut and edges, there is quite a lot of work here. For instance, Riccardo Rossi has some software for doing this kind of things. I'm not going to talk about that either. And then what we do is usually to use marching cube techniques in order to define and do some kind of meshing at every one of the cells in order to integrate on cut cells. So here I'm not going to talk about that. This is quite general too. I know that there are some complications in this part when we go to high order in order to keep convergence. That I'm not going to. This is not the point of the presentation today. The main point here is the ill conditioning of the system. So I told you we have very nice solvers for the linear problems for body-fitted meshes, but when we got unfitted, everything crashed. So we know that apart from the typical behavior of the condition number that goes with h minus 2, where h is the size of the finite element for second-order problems, we have also the issue of the small cat cell problem that here I'm sure everybody knows. The fact that when we have a cell in which the portion that's inside goes to 0, the condition number blows out and goes to infinity, and it's also very affected by the polynomial order that we are using here. So this one is something that we can deal with our preconditioners, but this is something new that we didn't have to take care of when we were working with body-fitted meshes. So we started in the first option. Our first approach to the problem was, okay, let's try to solve everything at the preconditioner level. Okay, let's define a preconditioner in parallel that will be efficient for this kind of problems. This is the first part. When we started to look at this with Frances Verdugo, we started with this approach. And the second one, which is the one I'm going to talk more today, is the one in which let's change a little bit the formulation and then let's use a more standard precondition. Okay? So with regard to the first approach, here we have 5 different geometries. We put these geometries, we embed these geometries in an O3 mesh, and we use our BDDC method. The one that works perfectly here if we would have body-fitted meshes. This is a weak scaling analysis, and here what I'm showing you is the number of degrees of freedom that we are having at every one of these systems. You see that we are solving larger and larger problems, and at some point, the number of iterations are unacceptable, and even the method that the solver does not even converge. If you apply the standard BDDC, BDDC is a type of solver. It's a domain decomposition solver, the one that we have in our library. I'm not going to get into details, but it's a domain decomposition. It's a scalable, at least 2-level domain decomposition solver. So the method fails when we go to this problem, and our first approach was, okay, let's see how we can solve the issues related to this domain decomposition solver. And we have a paper on that it's now accepted, in which we're able, for first-order problems, we're able to, in all cases, for all the geometries that we tried, to get a very robust preconditioner of the order of 10 iterations. And the remarkable thing here is that the number of iterations is almost independent of the geometry that we are using. Okay? I'm not going to get into details, but the idea here was to take the domain decomposition solver and change the continuity that we require between subdomains. Okay? Taking into account the fact that you can have unfitted cells. Okay? So the idea was that, and we were able to have a preconditioner that was very scalable for unfitted finite element methods. So this way we can go to larger scales, but when you go to second-order problems, it was slightly more difficult. But the main problem is even when you have to solve a local, at every subdomain you have to solve a local problem. This is even an issue, let's say, it's the same as we are in a serial computation. Because here we usually use direct solvers for the local problems in every subdomain, or for first-order methods we could solve the problem, the issue with diagonal scaling, and it wouldn't be so bad. When you go to higher orders, it's unclear how to solve it. So what we did is, okay, did you have this eta that, let's say, is almost very close to 0? What we do is deactivate somehow this cell. So these tricks are the what we need in order to make direct solvers work. Okay? But for instance, for second order, the situation is quite dramatic. Here you have the condition number. If we do nothing, we take a circle, we start moving it, and with in this situation are the red lines. This is for first order, the type of condition number that you get, and this is for second order. You see that this is like rubbish. The condition numbers here, we have a singular matrix at the end of the day in practice. Okay, so we said, okay, let's try to do something different, and then we started to use cell aggregation techniques. No? So here we have the interior cells. We also have the cut cells, the one that are being cut by the geometry. And here I put the degrees of freedom. This is like a first order problem, but everything I'm going to explain here applies for whatever order. So we know that to solve a problem here is good in terms of conditioning, but it's not good in terms of geometry. If we use an unfitted approach, we solve the right geometry somehow, but then the condition number of the system is really bad. So what we had to do here, what we wanted to do here is to solve the two issues, to have a good geometry and a good condition. So in order to do that, what we do is cell aggregation. So we take our cells. This is something that's very simple. We take our cells and we have a process in which every one of the cut cells is somehow, is the slave, is aggregated to one and only one interior cell. Okay, so this is a very simple algorithm that you can easily write in parallel, and after some steps what you have is something like that. Okay, so this is our aggregation. We don't control the way 3D is even harder. We don't control the geometry of this, but we don't care about that. So this is what we start with, and this is what people use, for instance, in finite volumes or in discontinuous logarithm methods, because the idea is that now they put the polynomial of order k in every one of the elements, and since they don't have any kind of continuity to enforce, that's quite simple to do. So this is what people usually use in DG methods, more or less. But we wanted to apply that with conforming finite element methods, in which we have, let's say, the right continuity on the interface between elements. Okay, it's a picture of the aggregates in 3 dimensions. And what we do here is the following. First, we did aggregation, as I told you. The second one, the ingredient that we need, is to define for all the vertices, edges, and faces in our geometry. Here everything is geometrical. Vertices, edges, and faces in our geometry that are, let's say, outside, are outer ones. We have to define, let's say, a mapping from the vertex, edge, or face to an aggregate. Okay? So we need to define this. This is a very simple thing that you can do. And then every one of these, for instance, this vertex belongs to this geometry here. This one only has one option. This one belongs to this one here. It is something quite simple. And now what we do here is to define aggregate base constraint. Now we go to our finite element space, and for instance, for this problem, which we have linear elements, we would enforce that our function here, let's say if P1, for instance, would be defined only by these 4 values. This would be constrained by the 4 here. Okay, so this, let's say, would be like a P1 polynomial. But then it would be enriched by the fact that this one and this one are not constrained in finite elements, so these one are free. So here we'd have additional finite element functions. Okay, so with this simple idea, we can define. It's very easy to include that in your code. It's very easy to define an extension operator that, given the values on the interior, given the function only on the interior cells, extends it to the whole, let's say, to the interior plus cut cells. Okay, so we define the finite element space that we're going to use is the range of this operator. Similar ideas were used for B-spline methods, and also a dot-based approach in this article here. Okay, so when we have this, for this kind of technique, we have a paper in which we analyze this framework, and we can prove, for instance, the condition number that is independent on the cuts. We can prove that we have the right approximability properties. We can prove that we have inverse and trace inequalities, H1 stability, H2 stability, the niche coefficients are bounded, etc., etc. We have done all the numerical analysis for this approach and prove that everything was working, and the experimentation tells us that everything works perfect. For instance, here we have first and second order method. This is the values that we get if we don't do anything. Now with this very simple aggregation, the condition number is independent on the mesh. So this allows us to have a much easier way to deal with the linear solver. This is the condition number of the condition number goes to h minus 2, as we have in body fitting meshes, so everything works as expected. This is error estimates, the one that we expect for first and second order problems. In 3 dimensions, we have implemented that in 3 dimensions too. And 3 dimensions, again, we see the same. This is the condition number in 3D for first and second order methods, and this is the cases that we have for instance, this is second order. If we don't do anything, we have here 10 to the 13. So you can see that it cannot be solved. This is again in 3 dimensions, 8 minus 2 for the condition number. The error estimates are the orders are the expected ones. And what we are doing now, we are almost about to finish, is we have included all the idea of cell aggregation in our HP adaptive parallel framework. And I have to say that this is not difficult because we have an odd tree mesh. We are using space filling curves. The space filling curves divide the mesh into as many processors as we have, and the linear algebra, which is the hard part in parallel, is not being changed with the aggregation, because let's say that the linear algebra only depends on the integer cells in our framework. We don't have any extra degree of freedom. So the linear algebra is independent of the aggregates that we're going to have. So at the end of the day, for going to parallel, the only thing that we have to do is, for integration purposes only, we have to move some cells, depending on the aggregates, a very small number of ones, and then do integration. So the parallel part of this is quite simple. The other thing that we're doing is to define the combination of aggregations due to the constraints and aggregations due to H or P adaptivity. This is something that's on the process, but it's also quite general. And then for this, we're using, as I told you before. So this is where we're about to finish now, which we're working now. And finally, some application of all this. We are in, as I told you, we're working on IT manufacturing processes, trying to simulate the thermal part for the moment of these kind of processes. How it works, we have, like, let's say, a machine in which we put a bed of metal powder, and we have a laser that melts some region of this metal powder, and then it's doing that in a layer by layer basis. Facing the laser, we are creating an object. Okay, so this is, let's say, IT manufacturing. It's an extremely hard problem because we have multiple scales, etc. I'm not going to talk about that here, but somehow the problem that we have to deal is, in this case, is simple, is a thermal problem, but the situation is that we have to deal with solidification, so it's a quite non-linear problem. So the main issue when we started working on this, as I told you, was the fact that the geometry was growing in time. So what we decided to use was to use body-fitted meshes. Okay, sorry, unfitted meshes. Body-fitted meshes were not suitable, and we decided to use unfitted techniques for that. And our approach to the problem is the following. We are combining our extremely scalable solvers, BDDC method that I presented before, and fitted finite element methods. Now we are using this cell aggregation, because with the cell aggregation, the preconditioner does not have to change. We can use the same preconditioner we're using for body fitted. We don't have to change anything, so it simplifies quite a lot the situation. And finally, since this is a problem which you have like multiple physics in the multiple scales, when you have the lasers, things are happening, everything is happening here, it is not happening much. So we need H adaptivity or HP adaptivity. So we are also doing that together with the Forest library. And this is like the example that we got some weeks ago. The thing is that what we do is that we define the geometry. We can read the same file as the 3D printer, let's say, as the IT manufacturing machine. And based on that, we create the scanning path. We read the same scanning path in our solver. So with this, we can start creating, let's say, simulating the same process as the IT manufacturing machine. Here probably you cannot see that, but here we have unfitted finite elements, and we have H adaptivity. For instance, here you can probably see that the elements are different at different regions. This is the same for another object in which we start creating the object this way. Here you have to think that around there is outer band. Okay. So this is what we did, even though for the moment we are in the validation stage of all this machinery, and for that we are using much simpler geometries, which is what the experimentalists tell us to do. For instance, we are now working with the Monash Center for IT Manufacturing in Melbourne, in Australia, and they do the experimentation. They have thermoplates here. They can evaluate which are the stresses, which are the temperatures at different points, and we use this. We use our simulations, as I told you, with complex constitutive models that have to deal with the solidification, and we compare what we are doing with the real experiments. So we have also an another article on this topic. So as a conclusion, our first motivation in order to start working on this was to eliminate somehow the structured mesh generation and also bring order the graph partitioning part. Another motivation was to deal with geometry, with growing geometries in additive manufacturing, and we combined our code with a highly scalable image generator, which is P-Forest. The problem was the singular linear systems, especially for second order methods. So if you don't do anything, domain decomposition solvers in parallel require tricks, and as you go to higher order problems, the situation is even harder. So now what we considered was to use cell aggregation that's very simple to implement, is robust, and it's very parallel, and work in progress. And the good thing that here you don't have to do anything with the preconditioner, you can use a typical one. And finally, the work in progress is to integrate this in a parallel HPLP frame. So that's all. Thank you.